So welcome, we're going to do the next chapter, which is energy of a system, and this leads on to the next chapter after that, which is conservation of energy. So these two kind of go hand in hand. Big ideas, well, work and energy, a scale of quantities measured in joules. So we're going to link work and energy from the very beginning. Work is what a force does. The effect of work through a distance, the effect of a force through a distance is work, and that work causes a change in energy on the object that the work has been done on. The force acts on an object. So energy is stored in an object, but work is done by a force. It's not good to say, I do work. It's one of my forces that is doing work. Okay. Work is performed by the displacement of a force. Work can be used to store energy in an object. Energy can be defined as the ability to perform work. Common types of stored energy. The ones that we deal with are kinetic energy, gravitational potential energy, and then spring potential energy. Those are the three that we work with. And the combination of those is called mechanical energy, as opposed to thermal energy, which we'll get to in later chapters. Let's start off talking about work. This is all caused by work, which is force through a distance. So the first thing to realize is that biology is very misleading. If I push, so my pushing force pushes this chair across the room, my pushing force is doing work. I'm putting energy into the chair, and you can see that because when I stop pushing, the chair keeps going because it's got kinetic energy stored inside it. Eventually the kinetic energy bleeds away because of friction. Okay, so force through a distance causes work. If I do force through a little distance, not so much work. Force through a bigger distance, a lot more work. So force through a distance is the amount of work. No distance, no work. If I simply push against the wall, no work is done by my pushing force. I biologically get tired. That's because my muscles are moving relative to, little strands in the muscles are flexing and all that. There is motion inside my body, but I am not doing any mechanical work. My pushing force is not doing any mechanical work, not because it's not trying, but because it's not displaced through any displacement. So you've got to have a force, and you've got to have a displacement. And it's not any old force times any old displacement. It's got to be the magnitude of the force and the magnitude of the displacement in line with each other. It's not a force and a displacement. It's got to be the magnitude of that force and the magnitude of that displacement in line with each other. And so we're going to use vectors to try and sort that out. We're going to start off with a constant force. Keep life simple, and then we'll do a non-constant force. So here's my basic picture. There's two ways of picturing this. I have a force. Yes, the force is not in line with my displacement. Sorry. The force is not in line with displacement. My force is off in this direction somewhere. And my displacement is in that direction. They're not in line with each other, and I've got to take that into account. I've got to accommodate for that. So I've got two choices. I can either take the component of the force that's in line with the displacement, or the component of the displacement that's in line with the force. And so in the first example, I chose to take the component of the force that's in line with the displacement, and so F at an angle theta became F cosine theta along the horizontal. And my displacement stayed as my displacement. So I ended up with F cosine theta times D. If I stay in SI units, so I'm in newtons and meters, my answer is in joules. So happiness. If I choose to, I can take the component of the displacement that's in line with the force. So I put my right angle there, and I recognize that this displacement component is d cosine theta. It's in line with the force, so now it's F times d cosine theta. can you see how numerically these are the same value? FD cosine theta, FD cosine theta. It doesn't matter which one you take, as long as you take the component of one in line with the other. You could even, I'm not suggesting you should, but you could even, if you were kind of feeling so perverse, you could even take each one's component in another direction and take those two and multiply them together, and you would get the same thing. So force and displacement have to be on the same line. Now, FD cosine theta, we can get mathematically by recognizing, ooh, shame on me, man, bad. That work is not a vector. Can you change that in the notes, please, if you have the notes? Work is a scalar. Work is always a scalar. So I can get a work which is a scalar from two vectors using the scalar product or the dot product. How many people have done the scalar or dot product? Anybody in math? Yeah. Okay, I'll teach you how to do it. In a bit. Let's do an example of this first. So, can you do that for me, please? Just do that. You know how to do this. Just do it for me, please. Do it quickly. Okay, so draw yourself a diagram. So here we have it, and basically, let's have a quick look, and yeah, people are basically saying A. And how did we get A? We got A by basically doing a decent diagram, and then basically we recognize that was 20 degrees. And I would prefer to say work is equal to F dotted with D, which equals FD cosine theta. So I look at my F, I look at my D, I look at the angle between, which is 20 degrees in that case. And this is 16.91 joules. So there's my answer. You know, conceptually, I'm saying it's 6 cosine 20 multiplied by 3, or it's 6 times 3 cosine 20, but either way, it's F times D times the cosine of the angle between. I'd like to be able to do things in 3-dimensional space, and so what I find is that it's really useful to talk in terms of the vector, the dot product, the so-called scalar product. When you have two vectors multiplying together, not a vector multiplied by a scalar, but a vector multiplied by a vector, you can have two outcomes. You can have a vector outcome, and you can have a scalar outcome. And this is a case where we have a scalar outcome. And that's a dot product. Dot, formal name is scalar product. So that tells you, to a great extent, it's a good idea to remember it by scalar product, because you know your answer has to be a scalar. But it's commonly called a dot product because that is a dot in between. And the cross product would be a big X. So A crossed with B is a cross product. A dotted with B is a dot product. And I've learned the hard way to put that as a big dot, not as a little period, but that's a big dot. Because if it's a period, you might miss it. Only happens with vectors, so we have a vector there and a vector there, but my answer is all scalars. And so let's learn a little bit about it. So basically, A dot B is the magnitude of A times the magnitude of B times the cosine of the angle between them. A dot B is the same as B dot A. The order does not matter. A dotted with vector B plus vector C is the same as A dotted with B added to the vector A dotted with C. So what's that called? That's distributive, I guess. And then if A is perpendicular to B, these guys are at 90 degrees to each other, then it's the cosine of 90, which is 0. If these things are parallel to each other, then it's just A magnitude multiplied by the magnitude of B. So parallel, big, perpendicular, 0. So get used to that, because with cross products it's the other way around. If things are parallel but in the reverse direction, A and B, it's the cosine of 180, which is minus 1. So we get minus AB, a negative value for this scalar. Whoa, what's going on? I pushed my chair in a positive direction with a positive force. I get energy put into the chair. Let's say the chair's coming towards me and I put my hand out to stop it. It pushes me back. So the displacement is still in the positive direction, but the force, my pushing force, is in a negative direction. Will I speed up the chair or will I slow down the chair? I'm going to slow down the chair. Have I added kinetic energy to this or taken kinetic energy away? If I slow down, kinetic energy is a half mv squared, less v means less kinetic energy. So, yeah, positive work means putting energy in. Negative work means taking energy out. So the very typical example that the books like to use is sliding into first space. Not that I've ever slidden into first space, I've never done it. But you slow down as you slide into first space because your displacement is in that direction, but your frictional force is behind you, and so you get less and less kinetic energy. We've done IJK, so it's worthwhile spending a bit of time. I dotted with I is going to be 1, because they're parallel. 1 times the cosine of 0 is 1. 1 times the cosine of 0 is 1. 1 times the cosine of 0 is 1. So those three, I dotted with I, and J dotted with A, and K dotted with K, equals 1. I, 1, dotted with J, they're at 90 degrees to each other, so that's 0. I dotted with K, 90 degrees to each other, so that's 0. And J, K, 90 degrees to each other, so that one's 0. So how do we do these? Well, basically what we do is we just take the component of the I multiplied by the component of the I plus the component of the J multiplied by the component of the J, and the component of the K multiplied by the component of the K. It's as simple as that. So a force of 3I minus 6J plus 2K newtons is used to displace a 5 kilogram object by minus 4I plus 2J plus 4K meters. Why is not the displacement in line with the force? Maybe the object had a velocity beforehand. Maybe it was coasting and I'm pushing it. It's not going to go in my direction unless I overwhelm it. It's going to go in some other direction. So that's the scenario. Okay, but well, it doesn't matter. What it matters is that I have a force, I have a displacement. How much work is done? I would say work is equal to F dotted with D, which equals the magnitude of F times the magnitude of D times the cosine of the angle between them. Why do I write down that whole thing every time? Because frankly, I'm going to remember it when I need it. If I only write it down when I need it, I'm not going to remember it. So I write down my equations often. Why do I put the arrows over the F and the D? After all, I know they are vectors. Yeah, but if you emphasize the fact that that's a vector and that's a vector, you won't mistake it for that and that. They're very different things. This is a vector force. It's an IJK thing. This is a numerical value. It's like breakfast and dessert. They're both foods, but they're not the same. Actually, it's even worse than that. It's like breakfast and the menu. They're both about food, but they're different aspects of a meal, if you like, you know? So they're different. So attention to detail really helps. If you're kind of like trying to tighten up on your writing and your layout and everything, it will pay dividends. If you still got the idea that this course is just about math, you're going to make more slips. It's not about math. The math is trivial. This is not a math course. This is sums for the most part. You don't get a job for putting numbers into equations. Anybody can do that. That's not being an engineer. So try and improve those skills that will make you into a better engineer. So better diagrams, better layout, attention to detail. Be like my brother and sharpen every pencil, you know. It's gonna make you a better engineer. He's a good engineer. So, what do? We say, okay, so W is equal to, let's write it down, 3I plus minus 6J plus 2K dotted with, make that dot big so you don't make a mistake on it. And it's going to be the displacement. And the displacement is going to be minus 4I plus 2J plus 4K. So you're going around and you're going to say, oh, work is equal to, it's going to be 3 multiplied by minus 4 added to minus 6 multiplied by plus 2 added to plus 2 multiplied by plus 4. Work is equal to minus 12 added to minus 12. Well, that's interesting. Added to 8 plus 8. So work is equal to minus 24 added to, with 8 added on is minus 16. Let's have a look. Boom, 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 boom. Oh, yeah. Yeah. Minus 16, E. What does that mean? Did I put energy into the system or take energy out of the system? I took it out. I slowed it down. The thing was kind of coming at this angle, and I pushed it in that angle, and we went off down towards the blackboard, but it was slowing down all the way from that. So, nice, informative answer. That little sign tells you a lot. Let's have a look. Ooh! This is a bit tricky. Let's visualize a force of 6 newtons pointing along the y-axis, positive y-axis. So here's my object, and here's my F equals 6 newtons, pointing in the positive y-axis. Is used to displace a 5 kilogram object by, so the displacement is equal to 3I minus 2J plus 4K meters. How much work is done? So let's look. My F. That's my D. I know what my D is. My D is 3I minus 2J plus 4K. And my F equals 6 newtons. And so I go, well, work is equal to F dotted with D, which equals FD cosine the angle between. So I try and do the first bit, but I don't have 2 IJK values. And I try to do the second bit, but I don't have the magnitude of the M, I don't have the D, and I don't have the angle between them. So you've got to go one way or the other. So what do you think? What would your gut feeling tell you is the way to go? Do you try to make the two things into IJKs and use the dot product, or do you try and find the angle and the magnitude and do the numerical way? A is dot, B is FD cosine theta. What does your gut tell you? Can you vote on that? I'm just interested in what you... There's no right answer on this. There's a good answer, but there's not a right answer. So are you going to try and go for the dot product? That means getting an IJK for that force. Or are you going to try and go the other way where you take that IJK and you make it into a magnitude and then you figure out the angle between the two of them? What do you think? What does your gut tell you? I'm going to push you on this because it's not a numerical answer, so I'm going to give you a 5, 4, 3, 2. Go on, number 20. Oh, man. My lips pouting. Number 20. Come on, number 20. Oh, well, never mind. So let's look. Oh! Truth be known, try it. Go home tonight and try it. And finding out, the magnitude is pretty straightforward. Figuring out the magnitude of this is not so bad. But finding that angle is a total nightmare. So, unless there's a really good reason not to, recognize, oh, this is just nothing in the x direction plus 6 in the y direction with the j plus 0k newtons. So get used to being, I'm not going to give you some wacky kind of thing. It's either going to be in the positive x, the negative x, the positive y, the negative y, the positive z, the negative z. I could do in the xy plane at 45 degrees, but that would be a long question. In principle, I'm happy just not giving you an axis direction. You know, I mean, I'll just not give you the ijk. This is hard enough for many folks. And so I say my work is equal to my F would be 0I plus 6j plus 0k dotted with, and then it would be 3I minus 2j plus 4k. So then we do, oh, okay, that's going to be work is equal to 0 times 3 plus 6 times minus 2 plus 0 times 4. Work is equal to minus 12 joules. Is that thing speeding up or slowing down? I'm taking energy out of it, so I'm slowing down. So watch out for that. You know, it's not often I give you an IJK and an IJK. I'm a teacher. I'm probably more often than not going to give you a direction with a magnitude and an IJK. And let you just figure out what you do for it. If you figure it out, great. Part 3, varying forces. So, all right, we've talked about a force and a displacement, and in the first bit, the force was not in line with the displacement. But it was a constant force. Now let's talk about a varying force. And to make it kind of manageable, I'm not going to have a different direction now. So now my force and my displacement will be in line with each other to keep things relatively straightforward. But the force is varying with displacement. So I push softly for the first 2 meters, then I push hard, and then I push soft again. Stuff like that. What's the overall effect? So I can represent this graphically. So I have force, and I have displacement. And remember what we did back in early chapters? We said, well, the slope matters, and so does the area under the curve. So let's think about area under the curve. It would be newtons times meters, and Newton times a meter, well, that's going to be like kilograms, meters per second squared, because that's what force is, MA, times meters, which equals kilograms, meters squared over seconds squared. And that's energy. And I just realized now I've done it that I've not told you what energy is, so I could tell you anything, but that's energy. So we get energy out of this by doing the force times the displacement. I should have explained it just like that. It's the force times the displacement. If the force is varying as displacement takes place, it's just the area under the curve. If it was a constant force times the displacement, you'd have a graph that looked like that. And you'd go 3 newtons times 4 meters, 3 times 4 times the cosine, if they're in line with each other, of 0, equals plus 12 joules. You just do the area under the curve. That's what you're doing graphically in that last section. Now we've got it varying. So you just got to do the same thing. It's just triangles, trapezoids, rectangles. It's just reading your axes. And we just got to say, well, let's make it 2 by 1. Notice I don't have the same scale on each axis because I'm an engineer. not a math person. We can't count the squares. I see a whole bunch of people, and they'll go, well, that's 1, 2, 3, 4, 5. Oh, that's going to be 6, 6.5. That's wrong, because on the x-axis, they're not equal 1, they're equal 2. So, because that's the way engineering works, you don't have the same axis. You don't have a simple axis on each scale. So you got to work these things out. So this is 2 times 1, and this is a half of 2 times 2, and this is a half of 2 times 1, and this is 4 by 2 because it's a rectangle. It's like that, and it adds up to 13. And I can tell you, this question is typically not so well answered. It's a skill you did way back in school, but it's not practiced very much. So can you do that one for me, please? What is the, actually I'm running out of time, so I'm going to do it. So what is the work done by the varying force during the first 8 meters? So notice, I'm not doing the entire journey. So let's be clear about what I'm doing. I'm doing 2 bits. I'm doing that bit. I'm doing that bit. Work equals area under force versus D graph. Tell that old guy that you know what you're doing. And then this is going to be the area of that. It's a trapezoid. So it's a half of 20 plus 30. That's the average height. Times the width is 4. And then the next thing is a rectangle. So it's the base, which is 4. 8 minus 4 is 4. Times the height, which is 30. So work is equal to, that's going to be 50 times 2 is 100 plus 120. So work equals 220 joules, if I did that right. So not hard. It's just you gotta care about it enough to practice, because you haven't done it for a long time. There's no point in finding out that you're a bit rusty on doing that in the test. So don't ignore it because it's like trivial. Just practice it. Let's get a bit more, this is supposed to be calculus-based physics, not, area under the graph-based, well, it's the same thing really, isn't it? So what's going on here? So we have a force which varies smoothly with displacement. And I want to know the area under the curve. So what I say is, consider work done by a force that varies with displacement. The work done by the force is equal to the area under the graph. Nothing new there. Remember that the units for the Newton are kilogram meter. I did the same thing I just did before. It's interesting. For one slice, there's my little slice, we can cheat and say, let's ignore the difference in the 2 heights. We can say, well, it's going to be the force times the width of the slice. And we're just going to do that for 1 billion slices and add them up. So this is the sum from the beginning displacement to the end displacement. That's xi and that's xf of that. And, well, we're going to get so skinny the slices are unmeasurable in width. So we say, in the limit as delta x goes to 0, my slice width goes to 0, my sum becomes an integral. I get the integral of fx dx. And that's a take-home. Work is equal to integral of fx dx. In fact, if you were to wake me out of a deep sleep and say, what is work? I'd probably tell you that work is equal to the integral of fx dx, because from this specific answer, I can simplify and say, oh yeah, and that means that work is equal to, well, that's going to be the force, if the force is constant, times the integral of dx, and that is equal to f times d, and I'm on my way. So some people remember the simplest form, and then they remember the more complicated form, and then they remember the more complicated form, and then they remember the complicated form. They're all saying the same thing, really. They're just different aspects, different variations. So I don't know 4 equations. I know 1 equation I can generalize about it. And that comes with time on task and practice and all that. So let's do something. So an applied force F is related to its displacement by this relationship. Okay. Where the force is in newtons and the displacement is in meters. What is the work done by the force? So work is equal to the integral of fx dx. Let's just visualize it a bit. So here's my fx, and here's my dx, and I go, and I imagine a little slice and all that kind of stuff, and I'm looking for the area under the slice. Well, okay, this is okay. It's going to be the integral of, well, the fx is not constant, so I can't take it outside the bracket. It's going to be 6 over x squared dx. Okay. So this equals the integral of 6 times x to the minus 2 dx. That's the same thing, isn't it? So work is equal to the, let's take the 6 outside, the integral of x to the minus 2 dx. And eventually I'm going to do it. That's going to be, let's have a look, increase the power by 1 and put it in the denominator. Now I need my limits. And I look at my question, it's from 2 to 8. So between 2 and 8. So I go, well, let's have a look. Let's write that one more time. 6. Let's do that one more time. 6 minus 1 over x. Yeah, the x to the minus 1 goes on the bottom, and the minus 1 might as well go on top, so it's that. And that's between 8 and 2. So work is equal to 6 times minus 1 over 8 minus 1 over 2, which equals 6 times minus 1 over 8. Let's make those two into a plus 4 over 8, which equals 6 times 3 over 8. I hope I'm doing this right. So this is going to equal 18 over 8. It's a positive 18 over 8, which equals 2.25 positive joules. So am I increasing or decreasing my energy? Increasing it. What am I doing? Let's visualize this a little bit. An applied force F is related to displacement. So this is a positive pointing force. And down here, it's relatively big because x is small. And here, it's relatively small because x is big. So my real graph should be that. It's big, and then it's small. And because this force is positive, the area under the graph is positive, which means that I am putting energy in. It's like a rocket, isn't it? I'm pushing with a really big force, and then as I get higher, my fuel is running low, and I'm pushing with less and less force. But I'm still increasing my kinetic energy, still increasing the energy in my object. In this case, it could be a mixture of kinetic and potential energy. I'm visualizing doing this from a planet. I really should simplify this and have it as a jet car. More people will get that right than will get that right. And that's sad, not because they shouldn't get this right. You will get that right. It's sad because this is an easy question and people are getting it wrong. They're throwing points away, so don't do that. Last little thing, I've got 3 minutes, so last little thing. I want to introduce the 3 forms of energy. You might have done this. Hopefully in Physics 1, you did kinetic energy equals 1/2 mv squared. And hopefully you did that, and really, frankly, truthfully, it's the change in kinetic energy, which I'll get to. And you probably did that potential energy equals mgh. And really, truthfully, it's the change in potential energy equals mgh. And you may have done that your spring potential equals a half kx squared. Okay? And what do you think? It's really the change in potential energy. And basically what we're going to do is we're going to introduce those three things. We're going to prove where they come from. And then we're going to use them. Now, it's easy to get carried away and get lost in the woods. So what I need you to know is the definition of kinetic energy, the definition of potential energy, and the definition of spring potential energy. But it is, in improving your skills, useful to try and figure out where it comes from. So I'm just going to talk you through this first one. We say work equals the integral of fx dx, and we know F equals ma. So let's substitute in. Work is equal to F applied times dx. That's the integral, isn't it? It's a constant force, if you like. F applied times my integral, times my change in displacement. Well, F applied is ma, so it's ma times the change in displacement. Well, I know that Vf squared equals Vi squared plus 2a times my change in displacement from my kinematics stuff. So my a times change in displacement is equal to a half F squared over half F squared final, a half Vf final squared plus a half Vf initial squared. Okay, so my work applied equals a half m times this, MAD. So I have a half m Vf squared minus a half mVf squared minus half mVi squared. Never noticed that before. And then somebody came along and said, maybe it was George Kinetic. It's a joke. There's no George Kinetic. But somebody came along and said, let's call this a half mv squared kinetic energy. And so we have K is equal to a half mv squared. Sometimes Ke, sometimes UK. Don't get tied into the letter. It's what it stands for. And this tends to be called the work kinetic energy theorem, because the amount of work you do is equal to your change in kinetic energy. The amount of work you do is equal to your change in kinetic energy. And it's tempting to think that there's only a work kinetic energy theorem. And that's not true. There's a work potential energy theorem. There can be a work spring potential energy theorem. It's not. It's the kinetic energy you're defining from this. It's not that the work equals it. It's that we can define kinetic energy from this. The work changes the amount of energy inside the system. When that is energy of motion, it can be called kinetic energy. Okay? So the take home is work equals the change in mechanical energy, in this case kinetic, and kinetic energy equals half mv squared, and try and look ahead, because we can make good progress on this bit. Cool.